All right, so let's go through and make sure that we have all the good ideas for our Pour It Out lab. All right, where do particles get their speed from? Okay, so we're going to be learning something about thermal energy. We're going to be learning about what temperature is, what thermal energy is, how it's moved, how it's transferred from one object to another. Okay, when we sat down to do the Pour It Out lab, you were able to control some things. You, as a lab team, were allowed to control a few things, right? What's something that your group should control as you pour the water? Things like the speed at which you pour the water, the height from one cup to another, right? The ability to keep the water in control and not spill, right? Um, things like making sure that only one person is the pouring person and that they mimic that cadence. They keep that cadence the same, that pattern of pouring. They keep that the same, right? There's lots of things in there. Just you can type any one of those in this spot. Okay. Now, the red text simply is the steps of how to do pour it out. So we've already done these steps, so you don't have to worry about the red text. In this area here, it just wants you to give your first 3 rows of data from your graph. So from your poured out graph document in your data table, just throw your first 3 rows of data in there. Okay. In the green box here, it literally wants you to copy and paste your graph from the poured out graph document. So go to your graph, just click it so that it's blue around all the edges of your graph, hit Control C, come back to this document, put your cursor right here and hit Control V. And you will paste a copy of your graph because you're going to want to see your graph at some points in time here to answer some of these questions. So right away, it starts with a question that is about your graph. So that's why we wanted you to have your graph there. What did the graph line tell you in the 3 water graphs? Well, here it's asking about your blue line. What happened to the temperature according to your blue line, right? It started to go up very quickly and then it started to level off and not go up nearly as much, right? The red line was the opposite, right? It cooled down very quickly and then began to level off and cool down not nearly as much. And the yellow line did something even different from the blue and the red, didn't it? The yellow line pretty much was a flat line, pretty much with very little change. So that is telling us that the temperature of that water represented by the yellow line didn't change very much. Okay. So you have 2 areas of water temperature, very different opposite ends of the spectrum here on temperature. They changed a lot and then leveled off. The yellow line hardly changed at all. So that's what you should be typing in here, that it changed quickly and then leveled off. The temperature was warming and then leveled off. The temperature was cooling quickly, then leveled off. And then here, the temperature pretty much stayed the same. Okay. Now, what did the graph line tell you about the speed of the water particles in the 3 graphs? Okay, so if we think back to our states of matter, we have solids, liquids, and gases. Okay, think about water as a solid. Okay, water is ice as a solid. So solids, their particles are linked together, they're bonded, and so they don't really like move away from each other. More, they kind of vibrate in place. So that movement is pretty slow, and the solids hold their shape pretty well, right? Compared to liquids and gases. So the ice water graph is telling me that the water particle speed is changing how? Well, if this water is in contact with ice, it's probably really cold. It's not quite ice, but it's probably pretty close. And ice, the particles in ice, don't move very much, right? So if the water immediately surrounded by ice is almost cold enough to be a solid, those particles probably aren't moving very much either. So if you start with ice water and start to pour it, and the temperature starts to go up, what's happening to the speed of those water particles? It's exactly what's going on in the shape of the line that you just drew. The water particle speed was slow at first, sped up very quickly, and then kind of found a rhythm and stayed in that same amount of particle speed. Boiling water was the same but opposite. That particle speed, since I poured that boiling water into your cup, that particle speed started very quickly, and then started to slow very quickly, and then found a rhythm that it stayed pretty much at the entire rest of the way. The room temperature particle speed, since it didn't cool or warm very much at all, that room temperature particle speed pretty much stayed the same. Okay, so that's what you're typing in these spots, right? Changed a lot, then leveled off, changed a lot, then leveled off, but in a different way, right? It started fast, slowed, and then leveled. And then this one, room temperature, didn't really move, didn't really change. Okay, all right, here we go. A1 and A2. Okay, so at the particle level, draw why the temperature of the water can decrease. Okay, so here's what you got to do. When you clicky, go down to edit so you can change these different arrows and symbols. Okay, we talked earlier about circles being water particles. Okay, if the question is asking you about temperature decreasing, so you're going to start with hot water, we have a way to symbolize how much energy a particle has, and we call these whooshies. These are the little black stripes for a particle that has very little energy, very little speed, very small amounts of heat energy. We give that particle a whooshie that's just a one whooshie. If it has a minimal or a moderate amount of speed, a moderate amount of energy, we give it two whooshies. We draw it out next to the particle. And then if a particle has a whole lot of energy, a whole lot of speed, then we draw three whooshies on the outside of that particle. Well, if this question is asking, show a particle diagram that explains how the temperature decreased. Well, that means you probably started with hot water, right? So hot water, that near boiling water, has the most thermal energy of the three temperature waters that we worked with. And what's happening is you're pouring back and forth, you're pouring water particles through air particles to get to the cup. So what's happening is you are pouring, and I'm going to use an arrow to show motion. This particle is moving that way. It has this much energy, and it's about to collide with and slip past air particles that are much cooler and have less energy than this water particle does. Remember, this water particle is near boiling. Is our air near boiling right now? No, the air is much cooler than that near boiling water. So this air particle right here only has one whooshie. So I'm going to quickly go grab a line. And I'm going to draw one whooshie. And I'm going to make sure that it's very thick so we can see it. Okay. And I'm going to grab it and I'm going to go bring my whooshie right there. So what's happening here is I'm pouring particles that have a lot of speed, a lot of heat, a lot of thermal energy through air particles to get to my other cup. Okay. So the air particles have much less. So what happens when these particles bounce off each other, collide, is after this happens, some of this energy that the water particle has, when it collides off of another particle, the energy, some of it, is going to get moved from the particle that has lots of energy to the particle that has little energy or less energy. So you're going to get this type of collision. And then after that collision, you're going to get a water particle that doesn't have three whooshies anymore. It has two. And you're going to have, as this water particle is on its way down past this air particle now, you're going to have an air particle that doesn't have just one whooshie anymore. It got two. It got another one because it ran into, it collided with, I'm trying to grab both of these. I guess I should do it one at a time. Now this air particle, because it got one from the water particle, now it has two. So by the time this water particle reaches the cup, and these are the cup particles, this is like the bottom of the cup, okay? By the time this particle reaches the bottom of the cup, it has collided here. It is passing now the air particle that it has already collided with. I'll move this over a little bit more to show that it's passing by. And it's on its way to the cup. This water particle now has a little less energy than it did before. It's moving a little slower than it did before because it bumped into another particle that didn't have as much energy. So some energy transferred from here to there. And you do that enough, you pour that 5 times, this water pouring through air that's colder than it is. Every time you pour, those water particles are colliding with air particles, and some of that energy is transferring from the water to the air around it on the way to the cup. And some of that energy is also transferring to the cup. So that helps to cool down this water even more, right? So here is what you are looking at whenever you have a particle model that needs to show how did the temperature of the water go down, because these water particles started with a lot of energy, bumped into air particles that didn't have a lot of energy, and then gave some of its energy to that particle, which now means this particle is moving a little slower. It has less temperature. It has less thermal energy. That's how water is cooling down when it's being poured through air that is cooler than it is. Now, I'm going to move all this back to where they should be because this is the template that, that you use. And I don't want to mess it up for you. So let me get it back to where it is. Okay, great. All right. So then explain what, so in words now, we're on A1, right? In words, what did you just draw is essentially what this is asking. Why does warm water get cooler when you pour it? Use these terms, right? Water particles that have a lot of energy are poured through and past air particles that have less energy. The particles collide. When they do, the particles that have more energy transfer some to the particles that have less, right? And we measure particle speed by taking a temperature of it. The temperature tells us really how fast the particles are moving. It's as if you are in a car and a police officer off to the side of the road is taking your speed with a radar gun as you go past to make sure that you're driving under the speed limit, right? So he's taking a measure of your speed. That's what miles per hour is. Miles per hour is a measure of how fast you are driving. That car is moving. Well, guess what? When you take a temperature, let's pretend this is that temperature probe, the thermometer. When you put that thermometer in the cup, you're actually taking a measurement of the speed that those particles are moving in. And how does it do that? Well, particles are bumping into the thermometer, just like they're bumping into each other. So as particles bump into that thermometer, the thermometer registers how fast are they hitting me, right? And it displays that as a degree in Celsius. So you're literally measuring the amount of speed, the average amount of speed of the item you're taking a temperature of. And in this case, it's water. All right. So A2 and then the explanation are pretty much the opposite. Because this question is asking, well, then if you are showing me how does temperature decrease, well, then what's a model that shows that temperature can increase? How does it explain that? All right. Well, think about the ice water. Okay. You're starting with particles that have very little energy and you're pouring them through air that has more energy than the particles, right? Is the air temperature 32 degrees? Is the air temperature 0? No, the air temperature is like a comfortable 71, right? But these water particles that were in the ice container, they're very, very cold. So when you pour them through air, the collisions still happen, but it's the air that transfers its energy to the water particle. So instead of starting with a 3 water particle whooshy or 3 whooshy water particle and drawing the same diagram you just drew, instead, you're going to start with a 1 particle whooshy, pour it through air particles, and show that the air particles have 3 to start with, and the water has 1 to start with. And when they collide, they both end with 2. But the water particle is actually gaining thermal energy from the air, making it warmer. And that's how we can explain why did the temperature go up. When we started with ice water and started doing this, we're pouring it through air that's far warmer than the ice water. So the air particles are transferring their energy to the water particles to make them warmer. And we can prove that by taking a temperature after 5 pours. whoa, wait a minute, the temperature is warmer than, or the temperature is higher than it was before. Well, that's where the water particles are getting their energy from. They're getting their energy from the warmer air particles. So it's still about collisions. Energy is transferred when two objects collide, and the one that has more energy transfers to the one that has less energy. That's essentially how it all works. Okay, so we're going to talk about these here coming up in a little bit. You'll use the Fusion book in your classroom to be able to do that. But we'll talk about now the actual definitions of thermal energy and heat, which is kind of the transfer of thermal energy is heat, and temperature. Okay, so we're going to try to keep these straight. All right, so let's get into the definitions then of these things, right? If you go to the pages that are being outlined here in your Science Fusion that you can use in the classroom, you'll find out that thermal energy is the total amount of kinetic energy in the particles of a substance. So you are looking at how much are all of these particles moving around together. What that is called is thermal energy. If it's moving a lot, that's a lot of thermal energy. If the substance or the particles are moving very little, then they have little thermal energy. Temperature is a measurement. It's taking a measurement of the speed of those particles. That's what temperature really is. So it's the measure of the average amount of kinetic energy in the particles of a substance. It can only be an average, and here's why. When you stick a thermometer in a substance and you want to take its temperature, the thermometer is only going to measure the speed of the particles that happen to bounce off of it. What if there's particles in that substance that are over here right now? They'll eventually get over to the thermometer to have the thermometer measure them, but they're over here right now. Is the thermometer measuring those particles when they're over here? No. It'll only measure the speed of those particles when that particle bounces off, collides with, and bounces off the thermometer. So because a thermometer can't measure all of the particles in a substance at one time, we have to call that an average, because particles are bouncing, hitting it, bouncing off, colliding, and then going away, while other particles right behind it smash up against the thermometer, bounce off, and go somewhere else. So it's only measuring the ones that are bouncing off it at that time. So that's why the temperature display shows these different numbers for a while until it starts to settle on one or maybe a little bit of variation, because these particles are bouncing off of it. And it's got to be like, okay, where am I about? Yeah, it's about this fast. So temperature is a measure of the average amount of thermal energy or kinetic energy in the particles of a substance. And thermal energy transfer, or we call this heat. Thermal energy is transferred, right, when a particle that has a lot of energy collides with a particle that has less energy. And that energy transfers from this particle to that particle. We sense that as, and we have a word for that called heat. If you think about it, the closer you walk up to a fire and you put your hands out to it, the more you're feeling energy transfer from the fire into your hand through the air, through radiation, right? So you're feeling heat because something that has particle energy more than you, it has more thermal energy than your hand, is sending that energy, transferring that energy through collisions into your hand. We call that heat. So that's what these definitions are. So when we're down here using Google draw a particle diagram showing what thermal energy, temperature, and heat are at the particle level. Thermal energy is just the total amount of kinetic energy in the particles of a substance. So you could just very quickly in this space, if you want to open up a Google drawing, that's great. You would open up the Google drawing and then you would just drop it in here. And you could just draw a bunch of particles, circles usually, with the same number of whooshies. That's thermal energy. So put some particles near each other, maybe it's a solid, and give them all like one whooshie. That's thermal energy. The total amount of whooshies of all the particles in a substance, that's thermal energy. Temperature, you probably want down here to go to Google Draw and draw like a temperature probe and have a couple particles touching the temperature probe and a couple particles not touching the temperature probe, so that it's showing that the thermometer is actually measuring the speed of the particles that happen to be colliding it. That's temperature, right? colliding with it, I should say. And then thermal energy transfer. The book calls this heat. You should probably draw a before and an after, like a before with a particle that has 3 whooshies and a particle that has 1, a collision, and then an after collision where both particles now have 2, right? So you can literally see the one that has more collides with the one that has less, and then after the collision, some energy has been transferred from the one that has more to the one that has less. You can do this with circles, squares, triangles, whatever. Whooshies are just lines in Google Draw, so it's not terrible. Okay. What is a word that describes what happens to thermal energy when it moves to a new place? We call this transfer. It moves from one particle to another. That's it. That's all that happens. Energy doesn't go away. Energy doesn't cease to exist. It just moves from one place to another. We call that transfer. There's a law that says energy cannot be created or destroyed. Right? This is called the law of conservation of energy. Where did the thermal energy from the hot water go if it was not destroyed? Well, you got a part of the answer by drawing the particle diagram. A lot of that energy from the hot water went into the air that it was being poured through. But there are some other places that energy went into. The energy of the hot water also went into the cup because those water particles contacted the cup because you're pouring it from cup to cup. So thermal energy went into the air around the water. It also went into the cup, right? And here's something that you might not realize, but as soon as you think about it, it makes a whole lot of sense. Some thermal energy from the cup or from the water went into the cup, warming up the cup. And then even that energy from the cup that came from the water went into your hand. And that's when you felt a warm cup. It's because the thermal energy kept being transferred into your hand, like my cup of coffee here. As long as the coffee inside there is hotter than my hand, and eventually the energy makes it to the cup as well, then I'm going to be able to pick this up and go, ooh, that's a hot coffee. I can tell because the cup is warm, right? It's even transferring into your hand. Thermal energy is crazy. So where did the thermal energy from the hot water go if it wasn't destroyed? To the air particles, to the cup particles, and even into your hand. Okay. It starts with a T. It transferred into the air particles, transferred into the cup particles, transferred into your own hand particles. Because, yes, you are made of particles. Okay, so that is a very brief explanation of the pour it out questions. And we're going to do another kind of like prep before our quiz that's going to cover states of matter and pour it out. So I hope this was helpful, and I will see you soon.